we're going to do today. It's going to feel somewhat like, not confusing, just more of an English class. There's going to be a bit of writing in this. Let's start off with some definitions. The first definition here, conjecture. Have we heard the word conjecture before? Yeah. Make a conjecture. It just means make an educated guess. All right. Where do we use conjecture? We use it in inductive reasoning. Okay, so we do two different types of reasoning in geometry. One is called inductive reasoning. The other is deductive reasoning. Most of what we're going to do in geometry is deductive reasoning. Deductive is where you base it on definitions and theorems. Inductive reasoning is basically looking at a number of examples to make a prediction. Often, inductive reasoning is used in like a science class. Yes. Oh, that's dark. That's not dark enough, huh? Here, maybe is this? Okay, I can make it darker too. So specific examples to make a prediction. So in a science class, like we're all in bio, right? So you do an experiment, you do the experiment over and over, and then you make a prediction based on that experiment. That's inductive reasoning. Okay, let's see. Eric was driving his friends to school down Ventura Boulevard when his car suddenly stopped 2 blocks away from school. We're going to make a list of conjectures that Eric can make as to why the car stopped. What would be, Zoe, what do you think?
The gas
Ran out of gas? Okay. Yeah, no. Car crash. Oh. Maya? Flat tire. Well, yeah, Maya. Oh. Oh, like hitting like maybe like a fire hydrant was going off and there was like a flood in the street. Traffic. Traffic would be my go-to answer because how much traffic do we? Well, why wouldn't we stop because of traffic? You're gonna drive through traffic?
Yeah, but like you'll keep going. But you could suddenly stop.
But like if
there's a block
and the cars aren't moving, he's stopping.
Yeah, he's got to stop. Okay.
I feel like that's not suddenly stopping.
Yeah.
Oh.
Getting pulled over.
If there's like a backup.
Getting pulled over. Boy, cheery. Okay, but we don't know any of the right answers unless we had more information to go on, right? So these are all a list of conjectures. What are some? So these are what we consider our educated guesses. Some conjectures that wouldn't make sense would be
spontaneous
combustion. What else? A herd of zebra crossing the street, right? Like that doesn't make sense in Ventura Boulevard. So we want to make sure when we're making our guess that it makes sense. Okay, now we're going to look at specifically a geometry/numerical example here. These are called triangular numbers because if you look at each set of dots, right, they make into a triangle. And basically, if we add one row, we should see a pattern. So the first one only has 1 dot, 3 dots, 6,
21.
10.
21.
Okay, so how are we getting 21, Zoe?
So the bottom line is 1, 2, 3, 4, 5, and then it's 6, and then 5, 4, 3, 2, 1.
So it's like adding 2, adding 3, 4, 5, 6. So that gives us 21. We don't have to make the next row of dots, but you can probably see. Anybody else see a different pattern? How to get that? Yeah, Jay.
Well, I just noticed that each of the bottom rows is increasing by 1.
Each of the bottom rows is increasing by 1. So we could look at the pattern in the numbers, or we could look at the pattern with the dots. Both of those are fine. Now we just have a set of numbers. So first we want to make a conjecture that describes the pattern. So we want to describe the pattern. And then we want to use the conjecture to find the next item. So the next number. And it's okay with the pattern. Sometimes there's like a little bit of weird. Let's see, 20, 16, 11, 5, -2, -10. Sometimes it's easier coming up with the number than it is describing the pattern. What do you think, Mia?
Well, the pattern is subtract 4.
Subtract
And
4.
then subtract 5 and then subtract 6.
Okay.
Subtract 7, subtract 8.
Okay, so we're subtract. So you could say subtracting 1, we could say additional number each time. Does that make sense?
Yeah.
So kind of increasing the number that we're subtracting by. And Mia, did you get that next number then?
So it's -19.
Negative 19?
Hold on, -18.
Negative 18? Let's see. So this will be -6, -7.
Oh, no. Wait.
We're going to subtract 9 from -10.
19.
-19. Good. All right. How about the next one? Anybody want to help me out here? Go ahead, Jade.
Each number multiplies by 1 more than the other.
Good. So this is like times 2 times 3. So now we're multiplying by 1 additional number each time. And I think this next number is going to be pretty big.
1,000, 10,000.
Wait, what is it?
10,080.
10,080? Do we have a second? I see a calculator.
I think it's
10,080.
10,080.
I think she was right. Right? Because what do we have to multiply 1,440 by?
7.
Good. Okay, any questions so far?
Hey, what's the next number? 10,080.
10,080. So 10080. Okay, next we want to look at counter examples. Okay, so we talked about the example with the car. We don't know what was the correct answer, but sometimes we can come up with a rule, okay, that's going to work in every case. And sometimes we can prove that rule doesn't work. And in that case, we just need one what's called counterexample. Okay, so a conjecture could be, we could just look at several observations. It might be true in most circumstances, but false in others. So it only takes one false example called a counterexample to show that the conjecture is not true. Okay, so in order for the conjecture to be true, it must be true in all cases. That's important. Now, when we do a counterexample, we can use detailed words or we can make a detailed drawing. Always make sure it's labeled because we want to be very specific. It's an example. Okay. So we're going to determine whether the conjecture is true or false. If it's false, we're going to come up with a counterexample. So we always have to be given a certain amount of information. So for the first statement, it says angle 1 and angle 2 are supplementary angles. Okay, so we need to have two angles that are supplementary, which means they add up to 180. So here's a conjecture. Angle 1 and angle 2 are both right angles. So we're asking ourselves, does that have to be true? No. Okay. So this one is false, right? So whoops. I keep forgetting. So that's going to be false. And now I want to come up with a counterexample. Now, we could write it out in words, or I can draw a picture. But what I need to be true, so this must be true, but we want to show it so that the conjecture is false. Any ideas how we could do that? Okay.
Draw like an X.
An
and
X,
then make it like kind of vertical.
kind of vertical, like that. Okay.
And then there's two acute angles and two obtuse angles. So
Okay.
like you can
So
make it
good. So so next thing I want to do, I want to be specific. What were my angles called? 1 and 2. So I'm going to label 2 of these angles, 1 and 2. Now, I'm not going to label the vertical angles because vertical angles are congruent, but I will label, let's say, these 2 angles. Now, I'm still not specific enough. Sammy? You got to give them values. So we want to come up with 2 values that add up to 180 that are not both 90. So what would be a good example for angle 1? What do we say? 70, that's fine. So we'll say this is 70 degrees. And then we'll make angle 2, 110. Done. Okay? Yeah, Maya.
Could you also do the one where it's like that and
Yeah.
like this one?
Absolutely. Absolutely. Now, I could actually even just say measure of angle 1 equals 70 and measure of angle 2 equals 110. Did I give you 2 angles that are supplementary? Did I make sure they weren't 90? So a drawing or just writing out the information, either one is fine. I usually like to draw the picture because I'm more visual. Let's look at the next one. Okay, points A, B, and C are collinear. Okay, so that means they all lie on the same line. My conjecture is that B is between A and C. A, B, and C are collinear. So we want to see. Now, could I draw this so this is true? Yeah. But the question is, could I draw it so that it's false? Yeah. Okay, so that makes the conjecture false.
So you have to make the conjecture false.
Well, if the conjecture is true, then I'm done. There is no counterexample. I could give you like an example of that would be, hold on. Let's say I told you A times B is equal to 0. Let's say that was given. And then my conjecture is that A or B equals 0. That has to be true, okay? The only way that we can have 2 things multiplied together to equal 0 is that one of them is equal to 0. So this is a true statement. Therefore, there's no counterexample here. I don't have to do anything else for that problem.
So will you give us stuff that we have to see if it's true?
Yeah, so the first part's going to be, is it true or false? So far the first one was false, so we...
A and or B equals 0.
And or, yeah.
Well, let's say we have like B on the homework, we could just say it's true.
Yeah. But it has to be true in every case. So remember up here, I highlighted, in order for a conjecture to be true, it must be true in all cases. Meaning there's no case where it wouldn't work. Right? So in the first example, I only gave you one example that made it false. Now, this is not the only example. We used 70 and 110. We could have used, what else? We could have used 80 and 100. We could have used 50 and 130. All of those would be fine. Okay, now counterexample here would be, I want to make the first part true. So I am going to make, I am going to make a line segment. And I want them all to be collinear. Now you can make it a segment or you can extend the line. That really makes no difference. I don't care. But I want to draw it so that B is not between A and C. Can I do that? Yeah, so I can make it A, C, B. Perfect. So as long as B is not in between them, we're fine. And that's all you have to do. So we just drew a picture for this one. You could also write it out in detailed words. I like the picture. To me, it's easier just to draw a picture.
Isn't the next one's true, right?
Is the next one true? N is negative number. Is n squared a non-negative number?
Yeah.
That's true. So again, if it's true, there's no counterexample.
If you square negative, what do you got again? You get
Positive.
positive, but isn't it like, you can't square root negative.
Yeah, if you have a negative number, like -3, and we square it, that would be 9, right? Okay, so as you can see, we're going to do 2, 3 because that was a really short lesson. Next, we're going to do conditional statements. Okay, conditional. What does condition mean? Not conditioner like for your hair, but...
Something that happens like based on something else. Like,
Okay, so like if your parents give you a condition, like if you unload the dishwasher, then you can go hang out with your friends, right? So there's a condition on the first part to see if you could do the next part, okay? So we think of that as a statement that can be written in if-then form. If you unload the dishwasher, then you can go hang out with your friends. If you buy a car, then you get $1,500 cash back. So these are just symbols. So the little arrow actually means something in mathematical terms. This little arrow here means if then or implies. So implies is the same thing as condition. Unloading the dishwasher implies that you can go hang out with your friends. Okay? Now, not all statements, conditional statements, are written in if-then form. So the first thing we can do, if it's not stated in that form, we can restate it. So a 5-sided polygon is a pentagon. So if, what?
A polygon has 5 sides.
Good. If a polygon has 5 sides, then it is a pentagon. All apes love bananas. So if an animal is an ape, then it loves bananas. All right, so 2 parts to the if-then statement. 2 parts. Hypothesis, that's the portion following if, versus the conclusion, that's the portion following then. So again, we use our if you unload the dishwasher. So unloading the dishwasher is your hypothesis. Then you can hang out with your friends. So conclusion is you get to hang out with your friends. So we're going to identify the hypothesis and conclusion of the statement. So if points A, B, and C lie on line M, then they are collinear. Now we're not going to include the word if. Zoe? Yeah.
points A, B, and C lie on line M.
Yep. And the conclusion, they are collinear. This is where I said it's going to seem like an English class for a moment. Don't worry, it still has that logic piece. It's a logic piece, so that's what makes
feels like a science class.
So that's what makes geometry unique in the mathematical world. There's a lot of this this writing aspect when we get to proofs. There's a logic piece to it. So it's not just solving equations, which again, that's why sometimes in the beginning of geometry it can be a little tricky because there's a lot of vocab. Okay, the Tigers will play in the tournament if they win their next game. Okay, this one's kind of stated backwards. What do you think, Zoe? Yeah, so what's our hypothesis?
Tigers win their next game.
There we go. The Tigers win their next game. So in the hypothesis, we want to be very specific. Oh, not the Tigers. We want to be specific as to what are we referring to? We're talking about the Tigers. What do we want them? What's the condition? They have to win their next game. So now what's the conclusion? Or Mia? Yeah.
They'll play in the tournament.
They will play in the tournament. So every once in a while, you have to pay attention to the way things are phrased. It might be backwards. Yeah.
Do you have to switch the Tigers in there because, like, they mean the same thing, and even if it said they won the next game, the Tigers will play in the tournament?
Yeah, it's just usually in the hypothesis we want to be specific because it's like this is following from what we're stating there. Just like when we said here, if a polygon, if what has 5 sides, right? It's a polygon. Okay. All right. Now we're going to take a conditional statement and we want to rewrite it in if-then form. And there's more than one way to write this. So rectangles have 4 right angles.
What if your shape is like has 4 right angles, but then it's like more sides? Then
So
then it can have 4 right angles. If it's concave.
Yeah.
okay, so that would be a different statement altogether. Our condition is what? What do we have? What's the first part? Rectangle. Okay, so if you have a rectangle, or if a shape is a rectangle, or if a polygon is, or a quadrilateral. So any one of those are fine.
Can I say if you draw a rectangle?
You can say that. If you draw a rectangle, you can state it real simple. If you have a rectangle,
Could I say polygon?
if a polygon is a rectangle,
I said it.
but make sure you have the word rectangle in the hypothesis.
Yeah.
Then
It will have 4 right angles.
it will have 4 right angles, where it has.
Oh, I said like if it has 4 right angles, then it's a rectangle. 95.
Okay, but is that saying the same thing? Because is there another shape that has right angles that's not a rectangle?
Yeah.
A square. So I want to, sometimes the statement is backwards, but unless the word if is in the middle of the sentence, we're going to assume it goes in the direction that we read it, like hypothesis, conclusion. Hypothesis, conclusion. So math teachers love to solve problems. Zoe, go ahead.
If you are a math teacher, then you love to solve problems.
There you go. If you are a math teacher, then you love to solve problems. Good. All right. Converse. Not the sneakers, but converse of a conditional statement. I kind of mentioned this word a few times because we actually had written it in our notes with some of our theorems. Converse means you can exchange the hypothesis and conclusion. Okay, so a converse is exchanging the hypothesis and the conclusion of a conditional statement. So here's an example. If 2 angles have the same measure, then they are congruent. The converse of that, notice I put 2 angles is the way I started. So if 2 angles are congruent, then they have the same measure. Okay. Now, not every converse is going to, both of these are true statements. Would we agree with that? Yeah. Not every converse is going to be true. So what we're going to do is we're going to take a conditional statement, write the converse, and then we're going to determine if it's true or false. Okay. So Maya, did you have a question or did you want to? Oh, you want to do the first one? Okay.
Can I say?
Sure.
If you are at least 16 years old, then they won't need a driver's license.
Okay, so if a person, or if you are, is at least 16 years old, then they have their driver's license. Okay, so if we look at the conditional, if a person has a driver's license, then they're at least 16 years old. That's true, okay? Because you can't get your license before you're 16. However, if you're 16, do you automatically have your license? No, so that's definitely a false statement. Now, here's where it gets interesting. We need a counterexample. So I'm sure someone in this room knows a 16-year-old without a license. Could be. Oh, we don't want to pick on them then. Oh, how about somebody that didn't even take their test yet? Do you know someone?
Well, I just said my uncle is 35 and doesn't have a driver's
Your
license.
uncle, what's his name?
Jason.
Jason. Uncle Jason is 35. Wow. Okay. That's okay. It's okay. He's our example without a license. Yeah, you could say somebody. So Uncle Jason is our counter example. That's okay. Wow. I mean, some people never get their license.
He lived in New York, that's why.
Well, especially depending on where you live. Yeah, New York makes sense. Sometimes people like from like parts of Europe or whatever where they're used to walking everywhere. Actually, I have my stepsister's husband doesn't have his license and he's like 45 because they live in a small Canadian community and they walk everywhere. There's no reason to have your license there.
I know, but like in California, I feel like it's impossible.
Yeah, it's really hard here for sure, especially in the valley, right? Like to get anywhere, you have to jump on Ventura or the freeway or something. Okay, let's do another one. Adjacent angles have a common side. Okay, we know, and I put that definition on your test. I hope I kept saying it over and over again. Some of you caught that. So they have a common side. That's not the whole definition, but let's start off with what would the
common ray and a common side?
Correct. But would you agree if two angles are adjacent, then they have a common side? That's true. Okay. But what if I say it the other way around? If two angles have a common side, now this is false. Okay, I need a counterexample. The best way to do this is probably to draw a picture. Okay, so I'm going to draw two angles that look adjacent to each other. So I'm going to draw two angles, and I don't know, I'll call this A, B, C, D. Okay. Now, I want these two angles to have a common side, but I don't want them to be adjacent to each other. So remember I said if they overlap, then they're not adjacent to each other. So I'm going to say angle. What would be one angle we could use? We could use the big angle, ABC. And now pick ABD. Yeah. Perfect. Oops, somebody's. So this angle and ABD, do they share a side? Yeah, this side right here. But are they adjacent to each other? No, because the big one overlaps the little one. Okay, so sometimes it's more than just drawing the picture because we have to identify which angles we're referring to.
Because ABD and DBC are
They share common interior points. So you could say they share common.
Isn't ABD and DBC adjacent?